As we mentioned before, grade 4, practice paper 1, and all of the practice papers are divided into
4
videos, right? 4 videos. And this one, as a matter of fact, A, B, and C, all those videos have the solution of 12 problems. The D video is a bit different. So we imagine that we have right here to solve another 12 problems. So let us begin. Because if we are doing 12 problems each time, so we have from 1 to 12, then we will have from 13 to 24, then we'll have from, after 13 to 24, we will have from 25 to 36. On the scale shown below, which number is at the point shown with the arrow? What number will be right here, Jerry?
4.5.
Oh, it is 4.5. Count this again. What do we have here?
It will be 5.
Okay, because we are beginning at 2 and we are going up by 2 each time. So that will be?
5.
Right, it will be 5. So the arrow is pointing on the mark that is approximately halfway between 4 and 6. See that?
Yes.
It is approximately halfway, or maybe we may look at it and say, because we cannot see the finer details of it, that it is halfway between 4 and 6. Because it is halfway between 4 and 6, what number will be halfway between 4 and 6?
5.
Right. So the correct answer is 5, and that is represented by option
C.
Right. Halfway between 4 and 6, we have 5. If we count with the numbers that we have there, we will realize that the numbers are going up by 2 each time. See? 2, 4, 6, 8. The numbers are going up by 2 each time. See? 2, 4, 6, 8. If the numbers are placed at the blank marks in order that we do not skip out any number, we will not be going up by 2 each time, but we'll be going up by 1 each time. So if we say 2, we do not skip a number and then go to 4. We say 2, 3, 4, 5, 6, 7, 8. So we are not skipping out any number. So 2, then 3, 4, 5, 6. So we'll do that. 2, 3, 4, 5, 6, 7, 8. And what do we know? We are correct. Here we see again that the arrow will actually point on 5, verifying that option C is correct. So right there, that's where we will be if we continue to count, not skipping out any number. We will still arrive at 5. Option C, as Jerry reminded me. Sophia ate 0.3 of a pie. She gave her brother 0.4 of the same pie. How much does she have left? Sophia ate 0.3 of a pie. She gave her brother what? 0.4 of the same pie. How much does she have left? We have there highlighted 0.3 of a pie and 0.4 of the same pie. What we have there is an indication that she removed. How many pieces of the pie did she remove?
2.
Right. She ate 0.3 and she gave her brother 0.4. So she removed 2 pieces of the pie. In order to determine how much is left, we first have to find the total portion of the pie that was removed. So we will take the root on this occasion to find the total amount of the pie that is removed. To find the total, what will we do to those 2 pieces of the pie that were removed?
Add.
We will add those 2 pieces of the pie that were removed. And those 2 pieces of the pie are?
0.3 and 0.4.
Right, 0.3 and 0.4. So we will add those. What do we say?
4 plus 3 equals 7.
Right, so we'll begin by adding the 10th digit. And Jerry says 3 plus 4 is equal to. And Jerry said 3 plus 4 equals 7. So in the 10th digit we will have 7. Do we say 0 plus 0?
Yes. Or not.
Okay, we'll add the 0, and some individuals use the word not. And it's a very long time that I've heard someone, maybe Jerry is older than I am, and I do not know. But it's a long time since I've heard somebody saying not. But before we add these, what do we do?
Put in the decimal point.
So we'll put the decimal point in its rightful place. So place the decimal point vertically below the others. We'll place the point vertically below the others in its rightful place. And what do we do next? Add the ones or unit digits. And we have 0 plus 0 is equal to?
0.
Right. So what we have done, we have taken the 2 pieces of the pie that were removed, and in order to find the total that was removed, we added those 2 together. Now that we have found the total fraction of the cake that was removed, we need to find the remaining portion. This we will do by subtracting the portion that was removed from the whole cake. So in order to find what remains, we add the 2 pieces together that were removed, and those will be the very large sum or the large portion that was removed. Then we will take that away from the entire cake. Does she have left? So we need to know what portion did she have left. What she has left is what remains when we subtract the portion that was removed from the whole cake. So we will remove the portion that was removed, and we will end up with what remains. Now, the whole cake is represented by 1 cake. So the whole is represented by 1. The whole is 1 whole cake. And we will take away the total that was removed, which is 0.7 of the cake. What do? We will say right there that we will subtract what? 7 from?
0.
Can we do that?
No.
What do?
You have to go over onto the left column and take away 1 from the 10th column, from the 1 column.
Right.
Bring it over to the
10th column. Alright, so that's correct. So 0 minus 7, we can't. So we go to the digit of greater significance and rename. So the digit of greater significance is this one here. But do not forget that what we have here is a decimal point. So this is a decimal fraction. Therefore, this column represents tenths, and this column represents ones. So we go to the ones column and we rename the 1 by removing this 1 And do not forget that when we are in this column, the digit of greater significance is 10 times. So the digit to the left is always 10 times the present digit. We are presently at the 10th digit, and we are getting assistance from the ones digit, which is immediately to the left. And when we do that, the digit immediately to the left is always 10 times the present digit. So there we have it. 10 minus 7, because that's what we have now. 10 minus 7 is equal to 3. What do we say next?
Bring down the decimal point.
Right, the decimal point must be placed vertically aligned with the others. So vertically align the decimal points. And what do we have there? Remember that this one was renamed. So we are saying 0 from 0. And the result is
0.
Right. So what do we have left? 0.3 of the cake or the pie, and that is represented by option
A.
Right. The correct answer is option A. In renaming, we consider that the place value to the left is 10 times the present one. The one that was removed from the ones digit is therefore 10 times 1 that is in the 10th position. So the 1's digit is what? 10 times the 10th digits, because in renaming we need to consider that the place value to the left is always 10 times the present place value. We have the same problem with the same detail. What do we do? If we can express the decimal fractions in vulgar form, sharing a pie may be easier. So let us do that. Instead of using decimal fractions, what do we use? Vulgar fraction. Right, so we'll have them in the vulgar form. So 0.3. How do we write 0.3 in vulgar form? When writing a decimal fraction in vulgar form, write the number without the point. So if we have 0.3, we will write that number without the point. So what will we write?
0.3.
We can write 0.3. But is the 0, which is a leading 0, is that going to have any effect on the value of the number?
Yes. No.
The leading 0, if we put that 3 there, without putting the point, we put 0 here. Does the 0 affect the value of the number?
No.
No. It will not affect the value of the number. Therefore, we do not need to keep the 0. As long as we are removing the point, we do not need to keep the 0. So when we are writing a decimal fraction in vulgar form, we write the number without the decimal point. So we have there 3. And we will place 1 in the denominator. So we write 3 and put 1 in the denominator. That is our first step. When writing a decimal fraction in vulgar form, write the number without the point in the numerator and place 1 in the denominator. Write the number without the point in the numerator and put 1 in the denominator. We are not finished yet. That is our first step. Count the number of decimal places in the number. How many decimal places do we have?
1.
So we only have 1 decimal place. So we count the number of decimal places in the number. The number of decimal places is the number of digits to the right of the decimal point. So counting the number of decimal places, we will only count the numbers that are to the right of the decimal point. Here we have the decimal point. How many digits do we have to the right of the decimal point?
1.
1. So we have 1 place of decimal. Right. So this here right, and the digit to the right of the decimal is only this 3. And we only have 1 digit to the right of the decimal point, meaning that we have 1 decimal place. That will be the same number of zeros in the denominator. So we have 1 decimal place. So how many zeros do we have here?
1.
Right, so we'll only have 1. 1 decimal place, 1 0. So 1 0. 1 decimal place, 1 0. So we have our fraction bar, the numerator, and we have the denominator. As a matter of fact, what did we do here? What did we do? In order to write that as a vulgar fraction, we put the 3 there and put 1 in the denominator. We count the number of decimal place, that is the number of digits to the right of the decimal point. We have 1. So there is only 1 place of decimal. So we have 1 accompanying 0 here. And we are through. So 1. And we have 1 place of decimal. So we have 1 0. So we have the fraction bar. We have our numerator as usual. And what do we have also?
Denominator.
We have also the denominator. The denominator tells us the number of equal parts that a whole is divided into. How many parts will the whole be divided into?
10.
Why? Because the denominator is 10. So the 10 represents the number of equal parts that the whole is divided into. So the whole is divided into 10 equal parts, as we have indicated in the denominator. So there is your whole, and your whole is divided into how many equal parts?
10.
10 equal parts. Our pi is in the shape of a decagon. A decagon is a 10-sided figure. It is already divided into 10 equal sections, or 10 equal parts. So there's your decagon divided into 10 equal parts. How do we know? We can count them. 3, 4, 5, 6, 7, 8, 9, 10. So we have the 10 equal parts there. So what we have established is that if we write the decimal fractions in vulgar form, then we can just share it up quite easily, because the denominator of the vulgar fraction will tell us the number of equal parts that the whole is divided into. The numerator tells us how many of the 10 equal parts we are talking about. That is, how many tenths we are talking about. So the numerator tells us how many of those 10 equal parts we are talking about. 0.3 is equal to 3 tenths. What does that mean? It means 3 parts out of 10. And 0.4 is equal to 4 out of 10, or 4 over 10, or 4 tenths, which means 4 parts out of 10. So Sophia ate 0.3 of the pie. And what is 0.3? 0.3 is?
3 tenths.
Right. 3 tenths. I'm happy to hear Jerry saying 3 tenths instead of just 3 over 10. Because we are talking about tenths as the number of equal parts that we have here, and 3 telling us the number of those equal parts that we are talking about. So 1, 2, 3. So Sophia ate how many?
3 parts of the pie.
Right, 3 parts of the pie. 3 out of 10 are 3/10. So 1, 2, 3. Sophia is gone with all of those pie. All those. Okay. So she's gone with all of those pieces of the pie, all 3 of them. She gave her brother Jerry 0.4. So what do we know? 0.4 will be what? 4/10, right? So let us also remove the 4/10 that she gave her brother. Take out 4/10 out of the remaining number of tenths. So take out 4. So count them off and remove them. They are gone. Remove 4 of them like that. And what is the question? How many tenths do we have remaining?
3.
Alright, so we can see that quite easily. 1, 2, 3. We have 3 of them remaining. 3/10 remain. We know that 3/10 is equal to 0.3. The correct answer is therefore option
A.
right. So as a matter of fact, we converted 0.3 and we got 3/10. Now that we have 3/10 remaining, we are sure that it is 0.3. Therefore, our answer is option A. Which would you use a ruler to measure? Would you measure the length of a pencil, the mass of a bag of flour, the temperature of tap water, the amount of milk in a glass? Which one would you use a ruler to measure?
Option A.
The length of a pencil. And Jerry is saying the length of a pencil, and that is represented by option A. So we have finished with the problem. We are finished with it. So it's done. There is your ruler. What is a ruler used to measure? A ruler is used to measure the length of something. The option that contains length is the correct answer. A ruler is used to measure the length of something. And we have the length here of a pencil. So option A is correct. But why do we put these in? Length, mass, temperature, amount. Option A contains length. It represents the correct answer. Notice that we are Xing out pencil. If we want to say the correct thing, we do not say that we measure the pencil. I am correcting some misconceptions here. Because we typically say that measure the pencil. The pencil has a few different attributes that may be measured. Because we can measure the mass of the pencil, we can measure the length of the pencil. So, we are not measuring the pencil, but we are measuring what? The length of the pencil. Neither do we say that we are measuring the flour, the water, or the milk. We're saying that we are measuring what? The associated things. So we measure things that are associated with those items and not the items themselves. So we are not measuring the flour. We are measuring the mass of the flour. We are not measuring the water. We are measuring the temperature of the water. And we are not measuring the milk, but we are measuring the amount of the milk. And the correct thing, instead of amount, what we should really have there is the volume of the milk, which is the amount of space occupied by the milk inside of the glass. So the volume is the amount of space that is occupied. And that is what we are measuring about the milk that is in the glass. We do not measure the pencil. Instead, we measure the length of the pencil. Also, we do not measure the flour. Instead, we measure the mass of the flour, and so on. Length, mass, temperature, amount. The aspect or property of an object that may be measured is called a quantity. We may call it a measured quantity or a measurable quantity. So length is a quantity because we can measure length. Mass is a quantity because we can measure mass. Temperature is a quantity because we can measure temperature. The amount, which should really be volume, volume is a quantity because we can measure volume. So what we can measure is called a quantity. Length, mass, temperature, and volume are all measured quantities. Some other measured quantities are time, area, and weight. So we have many measured quantity or measurable quantities. Different devices are used to measure different quantities. Depending on how large or small a quantity, for example, length is expected to be, we may have a variety of devices to measure those lengths. So a ruler is not the only device that can be used to measure length. And when you go to high school and when you are in university, you'll use things like these to measure length. A meter rule, a caliper, a micrometer, and so on. There are many different devices that may be used to measure length. And of course, the same is true about mass, because in a short while we will show you different devices that may be used to measure mass. One of those most popular instruments used to measure length is the
ruler.
That is the one that we use in class all the time. So we use a ruler to measure length. So there's your ruler, and we may use it to measure the length of the pencil because we just have the pencil in the option. And we say which one of these we may use a ruler to measure. And it turns out that it is the pencil. So let us measure the pencil. There's your pencil. And we will measure the pencil. How do we do that? Because we just don't take the ruler, put it on the pencil, and then any number that comes up in our mind, we just put that number down and say that is the length of the pencil. We have to be very careful when we are measuring. As we will see as we continue, you cannot just measure. You have to make sure that you measure accurately and you use your instruments correctly. The point of the pencil should not necessarily be placed at the edge of the ruler, because the zero mark on the ruler is most times not placed at the edge of the ruler. Neither should it be placed at the 1 centimeter or the 10 millimeter mark. So let us see what that means. If you look very carefully, you will see that we have the edge of the ruler right there, and a little above the edge of the ruler, that is where we have the zero mark. So the zero mark is little bit inside of the edge of the ruler. It is not at the exact edge of the ruler. So do not put the pencil at the edge of the ruler when you are measuring. put it at the 0 mark. The length of the pencil should be measured from the 0 mark on the scale of the ruler. And there's another word, scale. A scale is not necessarily something that you measure or you use to weigh or to find the mass of rice, flour, cornmeal, pork, chicken, and so on. The scale is the set of marks that we have here and the numbers together that you use to tell the value of the measured quantity. So the scale will be the marks and the numbers that we have here, from which we will read the length of the pencil. So the scale is not necessarily something to be used to measure or to find the mass of something in a shop or supermarket. So we have the scale of the ruler right there. And the scale begins at 0, which is right there, not at the edge of the ruler. So there we have where it begins. It begins just inside of the edge of the ruler. So the length of the pencil should be measured from the 0 mark on the scale of the ruler. Then take note of the position of the other tip of the pencil in relation to the scale of the ruler. So where do we put our next mark, Jerry?
At the tip of the pencil.
Right, so we will take a look at it by paying attention to where the other tip of the pencil is in relation to the scale. So there it is, right there. So we have 130 millimeters, which is the same thing as 13 centimeters. The length of the pencil is 13 centimeters, which is shorter than the length of a new pencil. And the length of a new pencil is approximately 18 centimeters. So there we measure our pencil, and we do not put the tip here at the edge of the ruler, because that's not where the scale begins. And we take a look at where the other tip is in relation to the scale, and we have it. So we will begin at the 0 mark, and then we have it at the other mark. We take note of where the other mark will be, and that is the length of your pencil. What do we have there? And I know what Jerry is going to say, that it is a scale. Right. Jerry is saying that it is a scale. But the correct name for that is a spring balance. What we have here is our regular spring balance, the one that we usually call a scale. It is a spring balance because it is operated on the inside by a spring. So there's a spring inside here that operates the balance, and it is called a spring balance. And the spring is extended right down to the tip inside there. So what will happen if we put captain's flour on the spring balance? And don't tell me that you put it on the scale. Where is the scale? The scale is this. Yes. The set of numbers and indicators that we have that will tell us the mass of the flour that we have there. So the scale is the numbers and marks, if we have marks there. If an item is placed on it, say a bag of flour, its weight causes the spring to stretch, which causes a mechanism to spin and turns the pointer and the scale. So what we do is we put the flour on the pan, and what will happen is that the weight of the flour will cause the spring to stretch, and the complete mechanism will cause also this to turn. So it will spin the mechanism inside that will also cause the hand, right, it is called the hand, to turn. And when it turns the hand, when it settles again, then we will know the mass of the flour. Right. So it keeps turning around until it is settled on the mass of the flour. Is it settled as yet, Jerry?
Yes.
Yes, it's settled. And it's settled on what mass? 2 what?
Kilograms.
Right, because when you are given a measured quantity, if it has units, then you must also include the units. Like when we do not include the units, our teacher used to ask us, this is 2 fried dumplings,
2 fish heads.
2 fish head. Right. So it is what? 2 kilograms. The position of the pointer is read from the scale, and that will be the mass of the item. Yes, it is read from the scale. It is read from this portion of the instrument which contains the scale. The entire object or the entire instrument is called a spring balance. Right. So we put the flour on the pan and we take note of where the hand settles, and that is the mass of our flour. The mass is therefore 2 kilograms. Before a spring balance is used, we have to make sure that the pointer is at exactly 0. Also, the entire instrument is not a scale. The scale is what we have right here. The numbers, and if we have marks that we use to tell the amount or the value of the measured quantity. And what people will do when they want to cheat you, they start their balance with the hand ahead. So the hand is not on 0. It is somewhere right here. Right, at the quarter line sometimes, as Jerry said, it's at the quarter line. And when they put it inside there, they give you less for your money. So you have to also make sure that when someone is using a spring balance, what they do is they make sure that it is on 0. And what they do sometimes when they have a spring balance is that when you are looking at the scale to see the mass, they use their hand and cause the mass of the flour to be heavy. So people will cheat, and that is some of the strategies that they use. But you have to be aware and make sure that you are given your correct mass. And this is your famous what? Balance. Your original balance. Here we have an ancient balance. To measure the mass of a bag of flour, we place it on one side of the balance. So there's your ancient balance, and we put the whatever it is that we need to measure the mass of, we put that on one side of the balance. And how do we determine its mass? The balance will naturally tilt to that side, right? Yeah. So if you put the flour inside there, what will happen? It will tilt. It will tilt to the side that the flour is on. Right. And to find the mass of the flour, what do we do? Different masses are then placed on the other side until it is balanced again. So we will put masses on the other side until it is balanced again. So here we put a 2 kilogram mass on that side. What happens when we put a 2 kilogram mass on that side? Both sides are balanced. And if we put 2 kilogram here and it balances, what do we know that this is? What mass do we have right here then? If we take 2 kilogram to balance this, then this mass will be what?
2 kilograms.
Right. It will be 2 kilogram also. So we balance this with a 2 kilogram mass. Therefore, the mass of Captain's flour that we have on this side is 2 kilogram. The mass that causes it to balance is equal to the mass of the flour. The mass that causes it to be balanced is equal to the mass of the flour. On this occasion, the mass of the flour is therefore 2 kilogram. And this one is the excellent balance that teachers use in our laboratory at school, and the nurses use this beam balance in finding the right in the clinics to determine the right. And some say to find the weight of the babies, but it is actually to find the mass of the babies. So it is not the weight that is being determined, but the mass of the baby that we are finding. So that is your beam balance. Now, this is a very simple version of the beam balance, because at school we have a triple beam balance there. Not only that, we might have a few more beams on the balance that the nurse uses. But all in all, the principle of operating the beam balance will be the same. This is called a beam balance because of the beam along which a sliding mass with a pointer is used to tell the mass of the object that is on the pan. That's a very long and sophisticated statement. Where do we put the mass? On the pan. And we have what? This is a sliding mass that is on the beam. And notice that the sliding mass has a pointer on it. So it is called a beam balance because of the beam, which is this beam, along which a sliding mass, which is this, with a pointer, there's a pointer on the sliding mass, is used to tell the mass of the object that is on. This is the pan. So let's go. The pan is where the object is placed. That is the pan. The sliding mass is used to balance the beam when an object is placed on the pan, and it is also accompanied by a pointer which will point to the mass of the object on the scale when the beam is balanced. So we have the sliding mass right here. As we see that the mass can slide in any direction and it can slide back again. The sliding mass has a pointer on it. What is the sliding mass used for? When something is placed on the pan, it is going to cause the balance to be unbalanced. Then we slide the mass and use that to balance the beam again. And when the beam balances, the pointer is pointing to the mass that it takes to balance the beam, and hence the mass that is on the pan. So let us continue. So there we have the scale, and the scale will be those marks, and on this occasion we do not have any number, but the marks on the beam that may be accompanied, usually it's accompanied by numbers, and that will be the scale. And the scale is what you look at in order to determine the mass of the object that is on the pan. So the sliding mass is used to balance the beam. So it has two purposes. The sliding mass is used to balance the beam. And when the beam is balanced, we use the pointer on the sliding mass to determine where we are on the scale, and hence the mass of the object that is on the pan. So the scale has the mark and numbers which give the mass indicated by the pointer. So the scale is what we just discussed with the marks and the numbers. A scale is not something used to measure mass or weight, but a portion of the instrument with the marks and numbers from which the value of the measured quantity may be determined or found. So this is the scale. It contains what? The marks and the numbers that we may use to determine or to tell the value of the mass that we are measuring. When the object is placed on the pan, the beam has to be balanced in order that the mass of the object may be accurately determined. So when you put the mass here, it will cause the beam to tilt. So when the object is placed on the pan, the beam has to be balanced. So you have to balance the beam again, because the beam is not going to be balanced when you put a mass on the pan. When the object is placed on the pan, the beam has to be balanced in order that the mass of the object may be accurately determined. The red arrow shows the balance point. So right at the tip, right of the arrow that we have here, is the balance point. And also we have a pointer here at the end of the beam, and this pointer must be pointing to the what? Balance point, which is the point of this red arrow that we have here. So here we have the beam, and the beam has a pointer. The beam is balanced when the tip of the pointer is pointing to the point, right, what we have here, the balance point. The red arrow shows the balance point and the pointer of the beam that points to it when the beam is balanced. Before any object is placed on the beam balance, it has to be balanced. That is, the beam balance has to be balanced. So you cannot put the object on the balance just like that. First, you have to make sure that it is balanced. The pointer on the beam must exactly be pointing to the balance point. So this is a pointer on the beam. For the beam to be balanced, it must be pointing to the balance point. The knob that we have right there may be turned in order to balance the beam if it is not already balanced. So when you are going to measure the mass of something, what do you do first? You ensure that the beam is balanced. If it is not balanced, what do we use to balance the beam?
The knob.
Right, so we use the knob to balance the beam if it is not already balanced. That is what this knob is used for. A scale is the set of marks and numbers on an instrument that are used to read the value of the measured quantity. I am emphasizing that, and that is why I am placing that right there again. Before attempting to measure the mass of an object, what do we have to make sure? That the beam is balanced. Right, so we make sure that the beam is balanced. The pointer on this screen must be pointing to the balance point. So this pointer must be pointing to the balance point. Place the object on the pan. Captain's flour. Put that on the pan. The beam will tilt like that. So when we put the flour on it, it will cause the beam to tilt. Right? So put the flour on it, and what will happen? The beam will tilt. When the beam tilts, what do you do? Slide the mass until the beam is balanced. Right, so we slide the mass until the beam is balanced. Right. The value that the pointer on the sliding mass points to is the value of the mass of the object that is placed on the pan. So the sliding mass has a pointer on it. It points to right here. And if you read it from the scale right here, the value, when it is accompanied by numbers, I did not include the numbers because it's too cumbersome on this slide. So if we put our finger right there, then that will be the point that represents what? The mass of the flour, if you should read it from the scale. In order to measure the amount of liquid in a container, we may pour it into another container. The more appropriate term for amount of liquid is volume of liquid. Volume of liquid. The volume of anything, whether solid, liquid, gas, or plasma, is the amount of space that it occupies. Right. So the amount of space that is occupied is called the volume. Right. We may measure the volume of milk in a cup by pouring it into one of those containers. So if we have an amount of milk in a cup, we pour it into this container or this container, and we will be able to tell the volume of the
Amount.
that we have, which is the volume of the milk, or the amount of milk that we have, or if it is water or some other liquid. So this one is a measuring cylinder, and this one is a beaker. So there is the milk in the container. So what do we know? In order to determine the amount or the volume of liquid in the measuring cylinder, what do? We see or take a look at where the liquid is in relation to the scale that we have there. So we have a scale right here that we can use to determine the value of the volume of liquid that is in that container. The volume of the milk may be read from the scale on the side of the measuring cylinder. So how do we measure the volume of the milk? We make use of the scale that we have on the measuring cylinder. But we cannot just look and just do it. There is a technique that we must use in order to determine the volume of liquid in any container. Those instruments are used in a laboratory. In the home, measuring cups are the ones most widely used. So when you're at home, we do not use measuring cylinders or beakers. We use what? Measuring cups. When a liquid, for example water, is placed in a container, the surface of the liquid is not flat. For all liquids, excepting one, the surface is slightly caved in, like in the diagram that we have right there. So the curved surface of the liquid is called a meniscus. So notice that the surface of the liquid is kind of curved in like this. The surface of a liquid in a container is not usually flat. It is curved, and it is called a meniscus. When it is curved in like that, it is called a concave meniscus. So the one that curves in is called a concave meniscus. In order to read the volume accurately, the eye must be on the same level as the meniscus. So your eye must be on the same level as the meniscus. The value of the liquid must be read from the base of the meniscus. So the meniscus is right there, and we measure from the base, not the top of the meniscus, but the base of the meniscus. And that is where we measure the volume from. So the volume is measured from the base of the meniscus. Now when we are reading the volume of liquid in a container, what do? We put our eyes, or a single eye, in line with the meniscus, and we read the volume from the base of the meniscus. The only liquid with a convex meniscus is mercury, and it is also the only metal that is a liquid. It is called quicksilver because it has a silver look and it flows very quickly. So mercury, which is a liquid metal, is called quicksilver because it has a silver look and it flows very quickly. So quicksilver. And that is the only one with a convex meniscus. Some measuring cups are used in the same way as laboratory instruments. However, some of them are of fixed volume. For example, we have an 8-ounce cup, or we just have one that is called a cup. So when you throw water inside there and you want a cup of water or you want a cup of cornmeal, you place the cornmeal in that cup until it gets to that single mark, because usually the one that is called a cup or an 8-ounce cup may just have a single mark on it, and it is accompanied by just a single mark because it is generally used to measure fixed volumes. So some of your measuring instruments at home will contain a few marks, some will contain only a single mark because it is used to measure fixed volumes. If we have a solid that sinks in water, we may measure its volume. So if the solid that we have, like a stone, it will go underwater naturally, then we may be able to measure its volume. What is its volume? Its volume is the amount of space that it occupies. Right, so we may measure the amount of space that it occupies. In order to read the volume, what do we do? The value of the liquid has to go inside there first. First, pour water in a measuring cylinder or some other instruments and take note of the volume. So, in order to determine the volume of a stone, which is an example of an object that will sink underwater, what do?
Put the object in.
We will put the object in water.
Yes.
But before we can put the object in water, we have to make sure that the measuring cylinder contains water. So, first, put the water in the measuring cylinder and what? Measure the volume of the water that we have in there. So, first pour water in a measuring cylinder or some other instruments and take note of the volume. What is the volume? Use a light and thin string to place the object in water until it is completely submerged. When we put the stone into the water, what do we expect will happen, Jerry?
The water will increase.
Okay, the level of the water will rise. So we'll have an indication of increased volume. So use a light and thin string to place the object in water until it is completely submerged. It goes in. As it goes in, the level of the water will rise. So we say that as it goes in, the level of the water rises. So as it goes in, the level of the water will increase. So take a look at it. There you go. As it goes in, the level of the water rises. Take note of the new position of the meniscus. So when the stone goes in, we need to take note of the new position of the meniscus. The volume of the stone is equal to the difference between the two readings. In order to find it, subtract the smaller reading from the larger one. So we have right there, the first volume was 20 centimeters cube, and the next one was 35 centimeter cube. If the volumes were as shown, then the volume of the object would be 35 minus 20, which is equal to 15 centimeters cube. It means that the object occupies 15 centimeter cube of space. So what do? We take a stone if we want to measure its volume, and we take note of the volume of water that is in the measuring cylinder first. Then, as we cause the stone to be completely submerged, the level of the water will rise. And what do? We take note of the new position of the meniscus. And if the first position was 20 centimeter cubed and the next one 30 centimeters cubed, then the difference between the two of them will represent the volume of the stone. An instrument that is used to measure temperature is called a thermometer. And some pronounce it like this: thermometer. Thermometer. So the temperature tells us how hot or cold something is. So we have a thermometer to be used to measure the temperature of a medium, or how hot or cold something is. The most popular thermometer is called a liquid in glass thermometer, which consists of a liquid enclosed in a glass casing. So the liquid is inside of this glass casing all the way up. The liquid can go inside here. And right here, notice that this is a larger place than the thin portion that we have right there. The glass contains a bulb that is like a reservoir which stores the liquid. The liquid is usually mercury that is easily seen, or alcohol which is colorless but may be colored red that it may be easily seen. So we have a liquid in glass thermometer which has what? Liquid inside of a glass casing. And right here we have the very large portion that is called the bulb. And then this part is called the bore. So as the temperature increases, the liquid expands and goes a longer distance inside the bore. As temperature decreases, the liquid contracts and occupies a shorter space inside of the bore. So here is our bulb with much alcohol inside there, and here is the very thin bore that goes up like that. And when we place this in a warmer area, it will cause the liquid to expand, and the mercury or alcohol will go up into the bore and occupies a longer region of the bore. When the temperature falls, or we place it in a region in which the temperature is very low, lower than the first one, the volume of the alcohol or mercury will get less. So the liquid will then occupy a shorter region in the bore. Then there is a scale from which the value is read. Of course, we know that our instruments that are used to measure must always have a scale. So there's always a scale, and your scale is right there with the marks. And as we shall see in other presentations, we will have numbers on the scale. But on this occasion, it is just enough to show you that the marks that we have there on the scale may be used to determine the value of the measured quantity. And in this particular case, the measured quantity will be the temperature. If you wish to measure the temperature of a medium, say the water that is inside of that beaker, make sure that the bulb of the thermometer is completely submerged in the water. So if we want the temperature of this water, what do? Put the thermometer inside there with the bulb completely submerged. If the water is warmer than the medium in which the thermometer is first located, then the liquid will rise. So if the temperature is warmer than where the thermometer was before, then the
liquid
in the bore will rise, because the warmer temperature will cause the liquid to expand. So there it is. So it goes up because the liquid is warmer than where the thermometer was first placed. And we need to place our eye on that level and look at the scale, and from the scale we will write down the value of the temperature of the liquid. So the temperature of the water will be the level of the liquid in relation to the scale that is on the thermometer. And that is what the scale is, to tell the value of the temperature that is being measured. Let us continue with problem number 28. Which is the best unit to measure the length of your classroom? Now your classroom is what you're about to measure. What unit should you use in measuring your classroom? Now how do you know the best unit to use and measure your classroom? Is it going to be kilometer, meter, millimeter, or centimeter? As a matter of fact, each one of these is a unit of length. Therefore, every single one of them may be used in expressing the length of your classroom. So, it is not that which one may we use to measure the length of your classroom, because all of them may be used. But which one is the best one? How do you know the best one? The best one is the one that is comparable to the length of your classroom, to the extent that measuring and expressing the measurement is quite practical. In choosing a unit to measure an object, the unit must be comparable, so that using it to measure the object is quite practical. So it makes sense and you can do it quite easily. Take note that the statement of the problem did not say which may be used. It said best. All of the units may be used because they are units of length, but which one is most suitable? Kilometer. Is that our correct answer?
yes. No.
We don't think so. And let us see why. How does a kilometer compare to the length of your classroom? We will take a look at the length of your classroom and compare it to a kilometer. What do we know that a kilometer is equal to? Let us use a real-life situation to tell how realistic it would be to measure the length of your classroom in kilometers. The track on which Usain Bolt runs is 400 meters all the way around, and the straight portion of the race is 100 meters. The length of your classroom is approximately 10 meters. Let us look at the size of your classroom in comparison to the track. So the track that Usain runs on all the way around is how many meters?
400.
That's a 400 meter track. And the straight portion that he's always running that fast race in, how long is that straight region?
100
meters. Right. So let us take a look at the track. There's your track. The track is 400 meters round, and the unit is that we are talking about is 1 kilometer, which is, if we are just taking a look at whether or not a kilometer is a good unit to use to measure the length of your classroom. So the track is 400 meters all the way around. And the unit that we are talking about is a kilometer, which is 1,000 meters. 1,000 meters is therefore 2.5 times around the track. 1,000 meters is therefore 2.5 times around the track. So what do we have here? This is your track, which is 400 meters all the way around. This straight portion of the track is 100 meters. And this is your classroom. This is what your classroom looks like on the 400 meter track. That is 100 meters. And how long is your classroom? Approximately 10 meters. 1 kilometer is 10 times the length of the 100 meter stretch. And the stretch is about 10 times the length of your classroom. So 1,000 meter makes a kilometer. So 1 kilometer is what? 10 times the length of this stretch that we have here. 1 kilometer is 10 times this. Because this is 100 meters. 100 into 1,000 is 10. So we take 10 of these to give 1 kilometer. And your classroom is what? 10 meters. It takes 10 of your classroom to be the 100 meters here. So 1 kilometer is 10 times the length of the 100 meter stretch, and the stretch is about 10 times the length of your classroom. So 10 times 10 is equal to 100. Therefore, 1 kilometer is approximately 100 times the length of your classroom. Now, if the kilometer is 100 times the length of your classroom, should your classroom be measured in kilometers?
No.
No. The kilometer is too large a unit to be used to measure the length of your classroom. So 1 kilometer is approximately 10 times the length of your classroom. To measure your classroom in kilometers is therefore unrealistic, because it is way too small in comparison to the unit of measurement. So your classroom is way too small in comparison to the unit of measurement, which is the kilometer. Therefore, it is not the most appropriate one to use. If you are in grade 4, then on average, a student in your class is slightly over 1 meter in height. In choosing a unit to measure an object, the unit must be comparable, so that using it to measure the object is quite practical. So it is practical, it has to be practical if the unit of measurement is comparable to the length of your classroom, which is what is being measured. So if it is quite comparable, in order that it is practical, then it is an appropriate unit to be used. So there we have a student standing, a boy, at the back of the class. That boy will be doing the grade 4 numeracy examinations in June of this year. From his feet, this is what a meter looks like. So notice that he is a bit taller than 1 meter. The length of the classroom is approximately 10 meters. it should be quite easy to measure something that is only 10 units. 1 meter is therefore a good choice. The correct answer is option B. So what we have is, we're just giving you an indication here as to what a meter looks like. And the classroom is approximately 10 meters. Therefore, it should be easy to measure something that is only 10 units. It should be quite practical. So 1 meter is therefore a good choice, or the meter is a very good choice. And the correct answer is option B. So the unit that we may use is meters, because the meter is comparable to the length of the classroom, to the extent that using that unit to measure the classroom is quite simple and quite practical. And we may look at the other units that are there, and the other units are centimeter and millimeter. Each finger of your hand has how many divisions?
3.
3 divisions. Being a grade 4 student, on average, each division is approximately 2 centimeters in length. So let us look at the divisions of your finger. We have 3 divisions of your finger, and each one is approximately 2 centimeters in length. Surely, a unit that is so tiny would not be the best unit in the option for measuring your classroom. Your classroom will be approximately 1,000 centimeters. So in order to measure or use centimeter to measure your classroom, you will be looking at using 1,000 of these units. So the centimeter is too small a unit to be used to measure your classroom. Well, it is not too small to be used to measure your classroom, but it will not be the best unit to use and measure your classroom, because it is not comparable to the length of your classroom, to the extent that using that unit to measure your classroom is easy and quite practical. So centimeter is too small a unit to be practical in this case, especially when we just have meter and the classroom is just 10 meters in length. 2 centimeters. Also, because there are 10 millimeters in 1 centimeter, your classroom will be 10,000 millimeters in length. Do not forget that each one of these is 2 centimeters. So 1 centimeter is just half of this, which is very tiny in comparison to the length of your classroom. Furthermore, if the centimeter is too tiny to be practical, the millimeter has to be 10 times less practical, because 10 millimeters make 1 centimeter. So your classroom will be 10,000 millimeters in length. Centimeter and millimeter are too small in comparison to the length of the classroom. Measuring your classroom in those units would not be as practical as measuring it in meters. So it is not which one may be used to measure your classroom. It is the best one. So you will use the one that is most closely related to the length of your classroom, in order that using that unit will be the most practical thing to do. And we find that the kilometer is too large a unit to be used, and millimeter and centimeter will be very small in comparison to your classroom. The one that fits right into it is your meter, because your classroom is approximately 10 meters long. So just 10 of those and you are done. Which is most likely to have a mass of 600 grams? So which one? Your sister, your lunch, a car, your pencil? Which one will have a mass of 600 600 grams. In order to understand what 600 grams represent, or an idea of what that mass is, then we will proceed to compare that 600 gram with other items that you have an experience with. There is your sister. Your sister, she has a mass of approximately 60 kilogram. So your sister is about 60 kilogram in mass. Kilo means 1,000. Her mass is therefore approximately 60 times 1,000, which will be what? 60,000 grams, which is 100 times the mass of 600 grams. So your sister will not have a mass of 600 grams because your sister has a mass of approximately what? 60 kilogram, which is 60 times 1,000. 60,000 grams. So your sister will not be close, or is not going to be likely to have a mass of 600 grams. A small pack of rice has a mass of 500 grams. That pack of rice is close in mass to your lunch. Your lunch will quite likely have a mass of 600 grams because you know that a pack of rice is close to the mass of your lunch, and the pack of rice is also close to the 600 grams. So your lunch will be close to the 600 grams, and your lunch is quite likely to have a mass of 600 grams, and that is represented by option B, your lunch. What about the others that are discussed? The car will have a mass that is over 1,000 kilograms. Kilo means 1,000. So we will have what? 1,000 kilograms and 1,000 grams in a kilogram. So the car will be approximately what? 1 million grams. So a car will therefore have a mass that is over 1 million grams. 1 million, not comparable to 600 grams. So we know that the car will not have a mass of 600 grams. It is not likely to have a mass of 600 grams. There's your pencil. The mass of your pencil is not even 100 grams. It is therefore impossible for your pencil to have a mass of 600 grams. So your lunch is the one that is most likely to have a mass of 600 grams. If n plus 5 is equal to 9, what is n? I always say that common sense is greater than mathematics, and I am always prepared to use my common sense rather than some sophisticated mathematical principle. And I'm going to make this statement that is a common statement that I make. If humanity had another way of administering a common sense examination, then there would be no use for mathematics. So mathematics is humanity's way of administering a common sense examination. And if there were another way to do it, then there would be absolutely no need for mathematics. So if n plus 5 is equal to 9, what is n? So there we have it. N plus 5 is equal to 9. When mathematics is expressed as we have it in what we have above there, in numbers, letters, and symbols, we call it an algebraic expression. Algebraic comes from the word algebra, which is the branch of mathematics that has to do with letters, numbers, and symbols. So when we have expressions expressed in numbers, letters, and symbols, that one is an algebraic expression. There are many types of expressions in algebra. However, because of the presence of that equal sign, we are sure that the expression is an equation. An equation has to have an equal sign. And by the way, it is not only an equation that will have an equal sign, but an equation must have an equal sign. Another thing that helps to make it an equation is that we need to find the value of an unknown. In this case, the unknown is n. So when we are required to find the value of an unknown, we know that what we are attempting to solve is an equation, especially with the accompanying equal sign right there. In algebra, there are many types of equations. The one that we have there is a linear equation. And we will not go so much into the ins and outs. Why is it called a linear equation and all of that? But the one that we have there is a linear equation. There are many different mathematical theories that may be used to solve an equation. But common sense is greater than mathematics, and we will attempt to use our common sense in solving the problem. In the expression, which number is the largest? So we have n plus 5 is equal to 9. Which number is the largest? 9 has to be the largest. Why? Because we add the other two numbers and the result is 9. Therefore, 9 is the largest number. If 9 is the largest number, can n be greater than 9?
No.
Can 5 be greater than 9?
No.
No. Well, 5 is surely not greater than 9. And n cannot be greater than 9. Because when we add 5 to n, the result is 9. Therefore, what do we know? 9 must be greater than n, or n must be smaller than 9. So when we find n, the result has to be smaller than 9. The one that is the sum of the other two, this one is the sum of the other two, and it has to be the largest. So there we have the two small numbers that add to give the large number, right? Since 9 is the largest, whatever we do in finding n, it must result in n being what? Smaller than 9. We will subtract 5 from 9. So what? Whatever we do, the result must be smaller than 9. So we are subtracting. Okay? So we will subtract. We subtract in order that the number will be smaller than 9. Because we have established already that the number has to be smaller than 9. So we have 9 minus 5. What is 9 minus 5?
4.
9 minus 5, and Jerry is saying that that is equal to 4. But in order to demonstrate that, we have 9 items there. And what do we do with those 9 items? We will subtract how many of them?
5.
1, 2, 3, 4, 5. How many are left?
4.
4 are left, as Jerry pointed out to us earlier on. Therefore, we are sure that our answer is option C. N is equal to 4. The correct answer is option C. Subtracting is not the only way to get a smaller number. But the problem has addition, and we need to do the opposite of addition, which is
Subtraction.
right. So if we add one number to another, and the result is 9, how do we find the other number? We will subtract 5 from 9. And that is how we will proceed. So we add 5 to a particular number and the result is 9. To find what that number is, we will then take away the 5 from 9 and we will end up with what that original number is. In the equation, the unknown is accompanied by 5 on the left hand side. That is what LH means, left hand. So we have left hand side right here, LHS, left hand side. Now we are solving this problem by making use of mathematical principles, which is the mathematical principles that we will use in solving an equation. So the equation that we have there has 5 accompanying n on the left hand side, and it is accompanying n by addition. As it is said right here, how is the 5 that we have here related to n? And we are saying that it is related by addition. It is related by addition. In solving the equation, the unknown is required to be the only thing on that left hand side. So when we are through in this equation, if we have solved the equation, the only thing that will be left on the left hand side will be this n. Therefore, in solving the equation, we need to eliminate or remove this plus 5 from the left hand side. How do we remove 5 from the left hand side? If 5 is added, how do we do that? 5 is added. If we minus 5 from the left hand side, then 5 minus 5 is equal to
0.
Right, and the 5 will be eliminated. So if we say subtract 5 here, 5 minus 5 is
0.
So the 5 is gone. So let us go ahead and subtract 5. So if we subtract 5, then the 5 will be eliminated from that left hand side. Since it is an equation, it means that both sides are equal. By subtracting 5 from one side, the equation is unbalanced. We therefore have to subtract 5 from the other side also. So what do? We subtract 5 from the other side also. So we just need to eliminate the 5 from this left hand side. Is that right?
Yes.
But if we subtract 5 from the left hand side, the equation is left unbalanced. Because what we do to one side, we need to do it to the other side in order that the equation will remain balanced. Right. So we subtract 5 also. So what we have there is we have n plus 5 is equal to 9. We need to subtract 5 to eliminate the 5 here, but we cannot subtract 5 from one side only, as the equation will be
Unbalanced.
Therefore, we subtract 5 from both sides. 5 minus 5 is 0. And if we say 0 plus n, the result will be n, because we are not adding anything to n, so n will return. So what we have is n plus 5 minus 5. The 5 is eliminated, and we also subtract 5 from the right hand side. So we eliminated the 5 there, but we still have 5 to be subtracted from the right hand side. N is therefore equal to
4.
Right, n is equal to 4. The correct answer is option C. Option C is the correct answer. 4. Now, we will just clarify what we have right there, or more so what we had on the previous slide. So what we have, or what we had on the previous slide, is the solution of the equation. But we have misconceptions going all the way through to university that we need to address right at grade 4 numeracy. What is that misconception? Let's see. We begin clarifying that misconception by taking note that most times mathematics students solve equations without including the intermediate steps because they are not necessary. So the intermediate step in this particular solution is left out. And there goes Jerry. Jerry's off. He's going home. So for the rest of this slide, we will not have anyone to help us to solve the problems. But this is the last slide that is in this section, so it is not going to be anything very negative for Richard James Mathematics Resources. So most times mathematics students solve equations without including the intermediate steps because they are not necessary. So we take out the intermediate step. So we have n plus 5 is equal to 9. The 5 accompanying the unknown is related to the unknown by addition. We need to eliminate it by doing the opposite of addition, which is subtraction. We will do the same to the other side. That is what we have here. 5 is added here, and we need to eliminate 5 by subtraction, which is the opposite of addition. But when we eliminate the 5 by subtraction, there is the other side of the equation that we need to subtract 5 from. Because if we do not subtract 5 from both sides, then the equation will be unbalanced and the equation, the solution of the problem, will be incorrect. So we will do the same to the other side. As a result, 5 is eliminated from the left-hand side, but we still need to subtract it from the right-hand side. So what happens? N is equal to 9 minus 5, which is equal to 4. So the intermediate step is gone. And because of the need to eliminate those intermediate steps, which is not wrong, students usually have a misconception. Because of this, students are tempted to say that the 5 that was added to the left-hand side is then subtracted from the right-hand side, which is not correct. The fact is, it was subtracted from both sides, which caused it to be eliminated from the left-hand side. But we need to complete the subtraction process on the right-hand side. So let's see what happened. N plus 5 is equal to 9. Eliminate 5 by subtracting 5. Cannot do it to one side, do it to both so that the equation can be balanced. When that happens, we have n is equal to 9 minus 5. So n is equal to 4. Students have a tendency to say that the 5 that we have added to the left-hand side is now subtracted from the right-hand side. Notice that the 5 that we have on the left-hand side, and know that we are subtracting 5 from the right-hand side. So students say that the 5 that we have on the left-hand side is now subtracted from the right-hand side. That is not entirely correct. The fact is, it was subtracted from both sides. But when we subtract it from both sides, the 5 will be eliminated from the left-hand side. and we need to complete the subtraction process on the right hand side. Let us continue with problem number 31. The temperature inside of the classroom is 27 degrees Celsius. It is 3 degrees hotter on the corridor. What is the temperature on the corridor? So here we have a situation in which we have two different temperatures. The classroom is 27 degrees Celsius. The temperature inside of the classroom is 27 degrees Celsius. It is 3 degrees hotter on the corridor. What is the temperature on the corridor? Hotter is our operative word. What does hotter mean in terms of the temperature of a classroom or the corridor? What does hotter mean? The important term in the statement of the problem is hotter. What does that mean as it pertains to temperature? Hotter means a higher temperature. The result will be larger. Therefore, whatever we find for the temperature on the corridor, it is therefore going to be a larger number than what we have in the classroom. So we have the temperature in the classroom is 27 degrees Celsius, and it is hotter by 3 degrees on the corridor. What is the temperature on the corridor? So the temperature that we have there is 27 plus 3, and that is equal to 30. The correct answer is therefore option A. The answer may not be as easy as it seems to be. Still, examine the statement closer. So, we are making note of the 27 degrees Celsius temperature that is inside of the classroom. We know the temperature in the classroom, which is 27 degrees Celsius. It is hotter on the corridor. We need the temperature on the corridor, which is hotter than in the classroom. The corridor has a higher temperature. So increase 27 by 3. Let us increase 27 by 3. That is what we intend to do. We have added 3 to 27, and the result is 30. So we imagine that we will still get 30. But we are trying to do it in more detail to give an understanding or a better understanding as to how we arrived at the answer. So we are at 27, and we need to increase that by 3. So count 3 more, and we need to count beginning at 27. So an additional 3 degrees Celsius will take us to 30 degrees Celsius. And the correct answer is option A. How many meters are the same as 4 kilometers? How many meters are the same as 4 kilometers? Now, how many meters, Jerry, are the same as 4 kilometers? I'm waiting on you.
4,000.
Okay, 4,000. So we have 4,000 kilometers. Why do we arrive at that answer? 4,000 meters. Let's see. Kilometer. kilo. Kilo is what we are focusing on this occasion. Kilo means 1,000. So 4 kilo means what? 4,000. A kilometer is therefore 1,000 meters. So where we see kilo, we may replace that with what?
1,000.
Right, we will replace that with 1,000. So 4 kilometers will mean what?
4,000.
So kilo means 1,000. 4 kilo means 4,000. So we may replace the kilo with 1,000. So instead of 4 kilo, we say 4,000. We may use the metric equation. 1 kilometer is equal to 1,000. Let's go again. 1 kilometer is equal to
1,000 meters.
So 4 kilometer will be equal to
4,000 meters.
right. So if 1 kilometer is 1,000, then 4 kilometer may be 4,000. Right. So what is 4 kilometer in meter? Maintain the consistency in the equation. The number that we have on the right hand side must correspond with 1,000 of the number that we have on the left hand side. So when we write an equation like this, 1 kilometer is equal to 1,000 meter. If we put 4 kilometer on this side, then we have to maintain the consistency in the equation. Therefore, we will have what? 1,000 multiplying by 4 on the right hand side. So whatever we find on this side, when we transfer or we convert, we will have what? 1,000 more, or 1,000 times. So we'll have 1,000 times 4, and that will be what? 4,000 meters. Right, 4,000 meters. To multiply 4 by 1,000, multiply the significant digits. And the significant digits are what? The 4 and the 1. We are multiplying 4 by 1,000. So 4 times 1, and that will give us 4. The number of trailing zeros will be the same as in the numbers that we multiplied. So when we multiply 4 by 1, and we get 4, or we are multiplying 4 by 1,000, multiplying the significant digits, we have 4 multiplied by 1, we will have 4. Also, we will have what? 3 trailing zeros in the answer, because the numbers that we are multiplying have 3 trailing zeros. So the answer will have 3 trailing zeros also. So there we have it. Option D, and that is 4,000 meters. We have a problem, or we have 2 problems that we are about to solve, and they include time. Not only the time that will be given on a circular clock, but the time that may be given digitally also. But it is very important for us to understand the circular clock. Therefore, we will spend a bit of time explaining how the time may be understood by making use of the circular clock. And not only the circular clock, but also if it is given digitally, we will show the necessary calculations that we need to perform in order that we may get the correct time in the end. But it is very important for us to understand things from the perspective of the circular clock, because when the time is given digitally, we do not have a system that we can follow, a practical system that we can follow in determining the time. So before solving the problem, let us clarify some conventions. The shorthand is what hand, Jerry?
Hour hand.
Right, is the hour hand. While referring to it, the difference in time between a number and its nearest neighbor is 1 hour. Therefore, this hour hand, if it is pointing on 12 and then it moves to 1, the time that would have elapsed will be 1 hour. And if it was pointing on 1 and then it is now pointing on 2, how many hours would have elapsed, Jerry?
2 hours. 1 hour.
Right. And if it is pointing on 4 and then it moves to 5, how many hours would have elapsed?
1 hour.
Right. The long hand is the minute hand. While referring to it, the difference in time between a number and its nearest neighbor is 5 minutes. 5 minutes. Therefore, if we are at 1, then we move to 2. That's a period by using this minute hand of what? 5 minutes. And if we are at 2, then we move to 3. Then another 5 minutes would have elapsed. So while going around by the hour hand, each number from one to the other is a period of 1 hour. That is with the hour hand. With the minute hand, if we move between consecutive numbers with the minute hand, the time is 5 minutes. The hour hand is between 8 and 9 o'clock. The hour hand, which is the shorter one, is between 8 and 9 o'clock. The time is after 8, or we may say to 9, because this hour hand would have passed 8. So it is after 8. And what is after 8 must be approaching 9. So that is before, or we may say to 9. If it is on 8, it's just 8 o'clock. If it is on 9, it's 9 o'clock. But if it is between 8 and 9, what do we say? It is before 9, or it is after 8. Right. In order to determine how long after 8, we will have to refer to the minute hand. At exactly 8 o'clock, the minute hand is on 12, which is no minute after 8. So, if it is exactly on 8 o'clock, the hour hand will be pointing exactly on 8. If it is exactly 8, the minute hand will be pointing on 12. And at 12, we have what? 0 minute. We may also take a look at it, depending on the perspective from which we are looking, that 12 also means 60 minutes. So, if we are talking about 60 minutes, is all the way around, and when it goes all the way around, it will, that is the minute hand, will go all the way around for 60 minutes. And 60 minutes make 1 hour. And because it is 1 hour, then this hand would have traveled from one number to the other. And we'll take a look at that also. The difference, not really difference, but we will understand how 12 can represent 0 minute in one instant, and in the other instant it can represent how many minutes, Jerry?
60 minutes.
Right, 60 minutes. So if the hour hand, like we have it right here, is past 8, in order to know how long after 8 we will need to take a look at the minute hand, because the minute hand is going to give us the minutes more precisely. So there we have an indication, not necessarily the minute hand, but we are demonstrating how the minutes are distributed all around the circular clock. We will count the number of minutes that we need to spend in order to get to the position of the minute hand. So in order, because right now, as we have the time right here, it is after 8. In order to tell how many minutes after 8, we'll have to consult the minute hand. That is what we are paying attention to. We have to pay attention to the position of the minute hand. But when it was exactly 8 o'clock, the minute hand was on 12. Right there. Which is 0 minute after 8. That is when this hand was exactly on 8. But we know that it is past 8. So in order to determine how many minutes past 8, we'll have to take a look at the minute hand. And we need to count the number of minutes reflected by the minute hand, and we need to count from the 0 position, which is on 12. So let us count the number of minutes. That is too quick, Jerry. Let's go. 10, 15, 20, 25, 30, 35, 40, 45. Right. So Jerry and I were counting in unison to arrive at the correct number of minutes. So the correct number of minutes, what again, Jerry? Let's count it again.
5, 10, 15, 20,
25, 30, 35, 40. Right. Good, 45. The 45 minutes is after 8. The correct time is therefore 8:45, and the correct answer is option B. Before solving the problem, let us take a look at the hands of the clock and see how they are used in telling the time. Which hand is that? The red one.
The hour hand.
Right. So the red hand is the
Hour hand.
right. So the short hand is the hour hand. The numbers on the clock are hours. The hour hand tells the hour of the day that we are in. It's usually shorter than the minute hand. So the shorter hand is the hour hand. It is stouter than the other hand. And the numbers that we have here are actually hours. So when the hour hand is pointing on a particular hour, we know that the time is exactly that hour. The longer hand, it is the slimmer hand, it is the minute hand. It is used to tell us what minute of the hour we are in. For the minute hand, the time between two consecutive numbers is 5 minutes. The time that it takes to go all the way around is 60 minutes. The time that it takes to go all the way around is 60 minutes. Right. Which are the number of minutes in 1 hour. How many minutes in an hour?
1 hour.
Therefore, the minute hand takes how long to go all the way around the clock?
60 seconds. 60 minutes.
60 minutes. And 60 minutes represent
1 hour.
right. So notice it going all the way around 60 minutes. So the minute hand will take how long?
60 minutes to go around.
All the way around. That's the minute hand. Also, the hour hand takes 12 hours to go all the way around the clock, while the minute hand takes 1 hour. So if the hour hand is to go all the way around the clock, which is a 12-hour circular clock, it will take 12 hours. When the hour hand is between 2 hours, we may say the time is after one of the indicated hour or before the other. Right here, the time is after 1 or before 2. We may even say it is to 2. So notice that this hour hand is not exactly on 1. Neither is it exactly on 2. So we say that it is after 1. And we also say it is before 2. Right, it is before 2. So it is either before or to 2. When the time is between 2 hours, the half in which the minute hand is located tell us whether to or after the hour is appropriate. So we need to divide the clock into 2 halves. So we have 1 half there. So if the minute hand is in the first half, going from 12 to 6, the after or past is more appropriate. So the time that we have there, since the minute hand is in the past or after side, we will say that the time is after 1. Now, technically, since 1 o'clock has passed, the time is before 2. But because it is in the first half, we will more appropriately say that the time is after. So after is more appropriate when the minute hand is in this half of the clock. If the minute hand is in the second half, which is going from 6 to 12, then 2 or before is appropriate. So the time that we have there indicated with that hand right there, if we change the minute hand around, the time that we have indicated would more appropriately be called before or to 2. So we have 2 sides, 2 halves of the clock. If the minute hand is in this one, we say more appropriately that it is past or after. If it is in this side, we say more appropriately that it is or before. Right. But as I said before, technically, if it is past 1, it is to 2. Right? And if it is not on 2 as yet, it is to 2, irrespective of which half it is in. So this time that we have, any time may be considered or even called to 2 or after 1, irrespective of which half it is in. But if it is in this half, it is more appropriately called after or past. But if it is in this one, it is more appropriately called to or before. If the minute hand is on 6, it is on half of an hour or 30 minutes. We may say that it is half past the hour. It is also half before or half to the hour. But we never usually say that. So we do not say half before or half to. We only say half past. Although technically it is half to or half before. But we never use half to refer to time that is before the hour, but time that is after or past the hour. We have shown how we may determine the number of minutes after a particular hour by counting the minutes in a clockwise direction. We did that counting like this: 5, 10, 15, 20, 25, 30, 35, 40, and so on. We have shown how we may determine the number of minutes after a particular hour by counting the minutes in a clockwise direction. The minute hand is on the to or before side, so the time is some minutes to 9. In this event, we count the number of minutes in a counterclockwise or anti-clockwise direction. So when the time is some minutes to the particular hour, because it is on the second half or the to side of the clock, then in order to count to find out how many minutes before or to the hour, we count the minutes in an anti-clockwise or right. Where will we begin?
12.
We will begin at 12. We will begin our counting at 12, which is the position of 0 minute. Right. And we will count in a counterclockwise direction. The number of minutes before 9 may be determined. So we will count the number of minutes until we get to the minute hand. Let's go again. 5, 10, 15. Right, 15. So 15 minutes. The time may therefore be read as 15 minutes to 9. Or 15 minutes before 9. A period of 15 minutes is a quarter of an hour, and those periods may be indicated on the to or past side of the clock. So 15 minutes, 5, 10, 15. 5, 15. So we have 15 minutes on either side. So if we have the minute hand pointing here, then the time will be a quarter to the hour. And if we have it pointing here, it is a quarter after or quarter past. When the minute hand is pointing on 3, we say that it is a quarter past the hour. And when it is pointing on 9, we say that it is a quarter to the hour. So right here we have quarter to, and there we have quarter, right? And those quarters are determined by which one of the hand?
The minute hand.
By the minute hand.
The minute hand.
Right. The time indicated is therefore quarter to 9. The 6th hour is halfway around the clock. When the minute hand is on 6, the time is half past the hour. Although it is also half to the hour, we never use half that way. When the time is given digitally, the number representing the minutes is in reference to the time after the hour. So we have our time given how? Digitally. The number that we have here represent the number of hours. And the number here represent the number of minutes. Not only that, the number of minutes on a digital display will tell us the number of minutes after the hour. So 8:45, it is 45 minutes past or after the hour, which means the same as 8:05 on the clock. Which one of these represent 8:05 on the clock? Is it 8 minutes past 5?
Yes. No.
Is it 5 minutes to 8?
No.
8 minutes to 5?
No.
5 minutes past 8?
Yes.
Right. As we discussed before, the time that we have here, the minutes that we have here, are the minutes what? After the hour. So any minutes that we have on a digital display, it is usually what? The minutes that pass the hour. So when the time is given digitally, the number representing the minutes is in reference to the time after the hour. So the first number before this, this one is in reference to the hour. And over here is in reference to the minutes. And it is usually minutes after the hour. The hour is 8 and the minute is 5. The 5 minutes that we have there tells us the time after the hour of 8. The time is therefore 5 minutes after 8. So the correct answer is
Option D.
right, is option D. Let us take a look at it again, which means the same as 8:05 on the clock. The time that we have on the clock, which is the circular clock, is the same as the time that is given digitally. The number of minutes is 5. So the time that we have on the circular clock is the same as this one. 5 minutes, right here is 5 minutes. How do we know that it is 5 minutes? Because we are looking at the minute hand, and this is the 0 position. And any movement between digits on the circular clock, if it is by the minute hand, it is a movement of 5 minutes. So 0 minute and then 1 click, we have 5 minutes. The minutes that are given digitally are after the hour. We will count our minutes beginning at the 0 position, which is at 12. And we only have 1 jump. Let's go. Just 1 jump right there. Do not forget that the first half of the clock is the pass or after side. The number of minutes that we have causes the minute hand to be on the pass or right. So we know as long as the minute hand falls in this half, we know that we are going to say appropriately that it is pass or after. Right. Good. So this confirms that the time is actually 5 minutes past 8, which is option D. We will not always have a small number of minutes like 5. So it is important that we understand. The first half of the clock is which side, Jerry?
The pass or after.
Right, the pass or after side. 5 minutes. Will 5 minutes end up in the pass or to side of the clock?
Pass.
Right. So the 5 minutes will end up in the past side. So we know that it is 5 minutes past 8. And the correct answer is therefore option D. The time on Stephen's cell phone is 2 hours and 45 minutes. 2:45. The time on Stephen's cell phone is 2:45. He expects a call in the next 20 minutes. When should he get the call? He expects a call in the next 20 minutes. When should he get the call? Let us see how that will be calculated. So there we have 2:45. 2 represents the number of hours, and 45 represents the number of
Minutes.
right. And the number of minutes is always given digitally after the hour. Right. The time on Stephen's cell is given in hours and minutes. The next 20 minutes will be 20 minutes later. 20 minutes later, an additional 20 minutes. we need to add 20 minutes to the present time. So the next 20 minutes will be 20 minutes later. So we need to add 20 minutes to the present time. So add the 20 minutes to the present time. What do we do? In adding the 20 minutes, we need to add minutes and hours. 20 minutes not accompanied by any hour. So a place holding 0 is placed in the hours column. So although we're adding just 20 minutes, because there is no hour, we place a place holding 0 in the hours column. So adding the minutes, what will we get?
65.
Jerry said 65. He's usually very quick with adding. He's really no midget with the digit. So 45 plus 20 is 65. It goes right there. This is 60 or more. We may get an hour out of it. So divide 65 by 60. When we add the minutes and it goes over 60, 60 or more minutes will be converted to hours. So we take the minutes 60 at a time for the hour, and if there is any remainder, then we allow those remaining minutes to remain in the minutes column. So 65 is greater than 60, so we will not leave the 65 minutes right there. We will convert to hours and minutes. If it were just 60, then we would not have any additional minutes left. So the 60 would go over as 1 hour. 60 minutes?
1.
60 minutes, 1 hour. Right. So 65 divided by 60 equals 1, and the remainder is 5. So we have 65 to divide by 60. So the remainder is 5. So we have 1 hour and 5 minutes. Right. So the 1, which is the quotient, will go in the hours column, and then the remainder will be placed in the minutes column. So 1 hour, we can get 1 hour out of this. And when we take an hour out of this, which is 60 minutes, 5 additional minutes will remain. And we keep them right in the minutes column. But the 1 hour that we would have received, we put that in the hours column. In the hours column, we have, well, we had 2 hours before. So with an additional hour, what do we have?
3.
Right. 3 hours. So the new time is 3:05, and that is represented by which option, Jerry?
C.
Option C. The resulting time is 3:05, which is option
C.
right. Now, what are we doing here? We are dividing the 65 by the 60. So let us see how 65 divided by 60 is equal to 1 and remainder 5. That's what we are taking a look at. Over on the next slide, what do we know? That when we have our 65 minutes, we say that is what? 1 hour and 5 minutes. So here we have 65 minutes, and we are dividing 60 into 65. We will begin by saying 60 into 65 will give what? 1 time. So 60 into 65, that will go 1. So it goes 1 time. Right. 1 multiplied by 60 is equal to 60. It goes there. And what do we do after that?
Draw a line, put in your subtraction sign, and then take away 60 from 65 is 5.
All right, Jerry, right on the ball. He said, draw a line, put in your subtraction sign, and then take away 60 from 65, and the result will be 5, just like that. So 5 will therefore be the remainder. There are 60 minutes in 1 hour. Therefore, when we add the minutes and it gets to 60 or more, for each 60 minutes period, 1 is added to the hours column. Any sum of hours that is greater than 60, we need to divide it by 60. The quotient will go into the hours column, and if there is any minutes left over, they will remain in the minutes column. And that we had on the previous slide. The time on Stephen's cell phone is 2 hours and 45 minutes, or 2:45. He expects a call in the next 20 minutes. When should he get the call? It is the same question, it is the same problem, but we are taking a different approach to its solution. So let us see how we will solve the problem entirely by making use of the circular clock. We may solve the problem another way by making use of the regular 12-hour clock. Stephen's time, which is 2 hours and 45 minutes, or 2:45, is already shown on the clock. So we have our clock there, and on the clock we have the time that is represented digitally on Stephen's cell phone. 2:45. How do we know it's 2:45? We'll see. He expects a call in the next 20 minutes. 20 minutes are to be added to the time. So 20 minutes later on. Therefore, we will have to increase time by 20 minutes. Let us move the minute hand an additional 20 minutes. So we have the minute hand here on 45 minutes. Here is 0 minute, is it?
Yes.
Let us count the number of minutes, Jerry.
5, 10, 15, 20, 25, 30, 35, 40, 45.
Right, so we know, right. So we know that is what? 45 minutes, or 2:45, correct?
Yes.
Right. So he expects a call in the next 20 minutes. When should he get the call? He will get the call 20 minutes later. We need to add 20 minutes to the time. So let us move the minute hand an additional 20 minutes. The present position is no movement, so we will call it 0. So right there. So that is where he is. And if we are going to say 20 more minutes, 20 additional minutes, right here is no additional minute. So 0. Let us go ahead and count the 20 minutes. So we will go ahead with the 20 minutes. 5, 10, 15, 20. So let's do it again. 5, 10, 15, 20. That is where we end up. The new position is just 1 digit after 12. And we know that for a minute, 1 digit is represented by 5 minutes. This represents 5 minutes by the minute hand. So for the minute hand, it is 5 minutes. So 1 digit means 5 minutes if we are counting by the minute hand. So there we go. Take a look at it again. 5, 10, 15.
20, 15, 20, 25, 20.
Right. So we are going to 20 minutes. And when we go 20 minutes, we realize that it is a single digit after 12, which represents 5 minutes. The minute hand would have passed 12. If the minute hand passes 12, it means that the hour hand must go past another digit. So the minute hand would have passed 12. The hour hand must therefore have traveled past the next hour. So every time the minute hand passes 12, the hour hand would have passed another hour. So the time would have passed 3. So let us take a look at that again. Notice that we were after 2. Then the minute hand goes past 12. It means that the minute hand must go past 3. And if we are past 3 and the minute hand goes past 12, it means that the time would have passed 4, and so on. The correct time is 3:05, or 5 minutes past 3. How does the clock show 2:45? Since the time is after the hour of 2, the hour hand must have passed 2 already. So for 2:45, the hour hand must have passed 2 already. So it has to show some time that is after 2. For the minute hand, the hour mark is 12. It also represents 0 minute. It also represents 0 minute. We will begin there and count 45 minutes. Let's go, Jerry.
5, 10, 15, 20, 25, 30, 35, 40, 45.
Right, 45. Notice that it started slowly and then went in a very fast speed. Let's go again.
5, 10, 15, 20, 25, 30, 35, 40.
Right, so that is where the minute hand should be. That is where the minute hand should be. Two or before. Do not forget that we have the 2 or before sign, and that is the second half of the clock. And not only that, we'll see something a little bit longer from now. Notice that the minute hand is also on the quarter of an hour mark on the before or to side of the clock. The time that is given is 2:45. It is also therefore a quarter to 3. So the time that we have is 2:45, and the minute hand is on a quarter of an hour to the hour. So the time that is given is 2:45, and it's also quarter to 3. Because notice that it is on the 2 side, and it's a quarter of an hour, which is represented by this minute hand being on 9. So it is a quarter to the hour. The area of each small square on the grid below is 1 centimeter squared. What is the area of the marked shape? That is your question, Jerry. What is the area of the marked shape? We can find the area of the marked shape quite easily. But while I was looking at this problem myself, I was just thinking that we need to show the grid lines in this shaded area. Then I looked at the standard that is set by the grade 4 numeracy, and I realized that they do not allow the grid to be shown. Therefore, we need to look at the diagram and be able to tell. Without making use of a grid in this region, we need to be able to tell, which means that we should be able to count the number of squares without having the grid lines there. So the area of each small square on the grid below is 1 centimeter squared. What is the area of the marked shape? The number of little squares will tell us the area of the shaded region. But their borders are not visible. So the borders for the squares that are in this region, the borders are not visible. How do we count them? Because we need to tell the area, and the area is going to be determined by the number of squares in that region. So we need to be able to count the squares. We will therefore count them using the visible squares as a guide. So the squares that are visible will be used as a guide to the squares that are not visible. So let us go straight ahead and do it. Let's go, Jerry. Notice that we have 4 right there. Then we have another 4, so that's 8. And then what else? 2, and how many more? Right. Right. So there we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 squares. And remember that we use the visible squares as a guide. So no one can say that we did that randomly or without any guide. So we arrived at our answer fair and square. Apart from counting and just say that we have 12 squares, so we have 12 centimeters squared, how are we sure? Which is option D. 1 centimeter square, that is the area of each square. So in order to tell the area of the entire region, we take the area of 1 square, which is what? 1 centimeter squared. And what do we do with it? We multiply that by the number of squares. So there are 12 of them, 12 little squares, each of which is 1 centimeter squared in area. 1 centimeter squared in area. So in order to tell the area of the region, we multiply the area of each square by the number of squares. And what's the number of squares, Jerry?
12.
So we have 12 squares. So 12 ones.
12.
Right. When we multiply by 1, the answer is the same as the number that we are multiplying. Any number multiplied by 1 is equal to that same number. So we multiply 12 by 1 and we get 12. So the result is 12 centimeters squared. And that is represented by?
Option D.
Very nice. Which 2 shapes make up this diagram? Which 2 shapes? What shape is this, Jerry?
Triangle.
And this one?
Rectangle.
Okay. That's right. So even if this is a square and you say that it is a rectangle, you are still correct because a square is a rectangle. The figure on top is a triangle. How do you know that it is a triangle, Jerry?
Because it has 3 sides.
It has 3 sides, Jerry. 3 sides. So that makes it a
Triangle.
And what do? We mark all of the triangles in the option with a blue rectangle. The lower figure has 4 sides. A figure that has 4 sides, what is it called? It is called a quadrilateral. Right, so Jerry is right on top of that one. It is called a quadrilateral. It is therefore a quadrilateral. A quadrilateral has 4 sides. It is a 4-sided figure. The figures in the options that are quadrilateral are rectangle and square. A square is a rectangle. So if you see a square and you call it a rectangle, are you correct?
Yes.
If you see a rectangle and you call it a square, are you correct?
No.
Not necessarily. So a square is a rectangle, but a rectangle is not necessarily a square. The lower figure is more certain to be a rectangle than a square. The one with both red and blue highlight is correct. Option C is therefore correct. It is a rectangle and a triangle. So this one is a rectangle and this one is a triangle. So if I call this one a rectangle, yet still it is a square, would I be correct?
Yes.
Okay, because a square is also a rectangle. Option C is correct. A square is a quadrilateral with all sides equal and all angles or vertices equal to 90 degrees. So in a square, all sides are equal and all of these vertices or angles are equal, and they are equal to what? Each equal to 90 degrees. But just looking, we may say that the figure is not a square because the sides are not equal. But I am just taking the opportunity to explain a few things. So we may say that this is a square, but it is not. But we are just saying that to explain a few things. So we will call it a square first, but we know that it is not. In a precise diagram, all of the equal sides are marked with the same number of strokes or dashes. So say we have this. How many strokes do we have here?
1.
So we have 1 stroke on this side. How many strokes on this side?
1.
How many strokes on this side?
1.
And so on. Because each side has a single stroke, we are saying that they all are marked in exactly the same way. Therefore, they are all equal. And the figure that we have there is a square. Because if all of them are marked with a single dash, then all sides are equal, and that would make it a square. Now, sometimes students look at a diagram. All sides are equal, but it is not something that it is good to arrive at that conclusion with the naked eye, without assistance. So examiners or expositors generally, if they intend you to call something a square and they don't want to put in the measurements inside there, they mark all sides with a single dash, and that will tell you that all sides are equal, which will make it a square. According to the dashes that we have there, it would mean that the quadrilateral is a square because we have 1 dash on each line. Each side has a single dash, which tells us that they are all equal. Since the quadrilateral is not a square, but is a rectangle, only opposite sides of a rectangle are equal. So opposite sides should have the same number of dashes. So if this is a rectangle, then this and this should have the same number of dashes, and then this and this will have the same number of dashes. There we go. Now we are sure that it is a rectangle because these two sides having different number of dashes means that these two sides are not equal. But these two sides are equal because each one of them has how many dashes?
2.
Right. Each one of these has how many dashes?
1.
Are these two sides equal?
No.
No, because they have different number of dashes. Are these two sides equal?
Yes.
Right. And what we have here, opposite sides with the same number of dashes, we are sure that it is a rectangle. Although it is not the case here, sometimes it is difficult to tell if a figure is a square without measuring it. Because a square is a rectangle, if we say that the figure is a rectangle, we are sure to be correct. So, if we are not sure and we don't have any dash on the sides, and it looks like a square, and it looks like a rectangle, because a square is a rectangle, if we call it a rectangle, then we are sure to be correct. If a figure looks like a square, but we are not sure, if a figure looks like a square, but we are not sure of the measurement of the sides, then we may say that it is a rectangle to be on the safe side, because a square is a rectangle. So if it is a square and we call it rectangle, we are still right.